In this example, we're going to work on kind of an interesting one. We're in the by parts section, so you were probably guessing that we want to use by parts, but this one's a little strange in that I don't have a product. I do, however, have something that I absolutely don't know how to integrate off the top of my head. I know the derivative of arctan is going to be 1 over 1 plus w squared, but I don't have any clue what the antiderivative is, so I can't just jump right to it. I have to do something. So this is a case where what I just said about the derivative is helpful. The derivative of this function is actually fairly nice to work with. So what I want to do, and Lai would confirm this, is say that the inverse trig function is going to be my u, which means my du will be a 1 over 1 plus w squared. I'm just going to stick the dw in the top. So again, just with the notation stuff, here u is a function of w. So down here, I'm going to be taking the derivative of u with respect to that variable w. And then I just move the dw up to the other side. Okay, and then my dv is going to be a dw, which means that my v will be a w. When you find the antiderivative of dv, you get v. Finding the antiderivative of dw will give you w. Okay, so there's my by parts. And then we're going to put it back together and see if this is at all helpful. So sometimes even when it doesn't really look like a product, it's possible that it's a good choice. So right now I have, u times v minus the integral of v du. I'm going to move that dw back out to the side. Okay, so we have w times 1 over 1 plus w squared. We can move that w up to the top. So I don't know if this immediately jumps out as being something easier to deal with than the arctan originally was, but basically what we have there is a really nice substitution problem. So we're going to jump from here. Oh, I was so rude. I used w's. So we're going to use z's. We're going to do z substitution. What I'm seeing is that this denominator we could think of as being the inner function in a composition of 1 over x and 1 plus w squared. And that's really promising because if this is my z, then my dz dw is equal to 2w, and I do have an extra w floating around. So I'm going to say dz divided by 2 is equal to w dw. So now I'm going to be replacing this with a z, and I'm going to replace this pair with a dz over 2. Okay, so at this point, I'm going to move over just a little. I have, what do I have? Okay, I guess I'll keep my color. I was thinking I was going to be clever and helpful with my colors, but I don't know if it matters here. Okay, so I have the integral of dz over 2w, or 2z, sorry. You can move the 1/2 out in front, which again I think does make life a little easier. People try and do kind of wacky things if they leave it in there. And we're just integrating 1 over z with respect to z, which actually is a really common one for people to mess up. Who do I take the derivative of to get 1 over z? The answer is the natural log of the absolute value of z. People are trying all the time to use power rules on that. So I have a w, arctan w, minus 1/2, let me make that look more like a 2 since we have z's as well, 1/2 the natural log of the absolute value of z plus c. Okay, and then the last thing will be to substitute back in the w's. So here we'll go back to my original color even though I wasn't very consistent with it. So I have a w arctan w minus 1/2 of the natural log of the absolute value of 1 plus w squared plus c. And again, it might look like a terrible plan, but these actually tend to not be that bad to take derivatives of. So anytime you're feeling like you don't quite get it, try taking the derivative and just see what happens. It can sometimes be really helpful to go backwards.